Welcome to today's webinar. The topic today is design of timber frame walls in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the Dlubal website, German and English webinars, newsletters, customer projects, and so on. I will be the moderator today, and I will answer your questions during the webinar. And Bastian Kuhn will be the presenter. But Bastian, you can introduce yourself. Bastian?
Thank you for the introduction. My name is Bastian Kuhn. I'm responsible for the development of our software in the field of timber design, such as cross-laminated timber or timber frame walls, and structural design of beams and surfaces made from timber, and also for the building model add-on.
Okay, thank you, Bastian, for your introduction. Then we can switch off our webcams so that the attendees can see the full screen. You can ask questions when you click on that button with the question mark. Then you can enter your question here, and with pressing send, I will receive your question. And I will answer you. You can also watch the entire webinar and then email your questions to info@dlubal.com. Okay, then I take over or hand over to Bastian. He will introduce the agenda. Bastian, you can start.
All right. So what I want to show you today is the definition of timber frame walls with the thickness type beam panel on quite a simple model. And then once we've done that and analyzed it, we will go further and do the analysis in a complete 3D model. And I will show you the detailed analysis of timber frame wall, what is going on when there are openings inside the timber frame wall, or if you have a special geometry with which is maybe not only containing 4 lines. Okay, I will share my screen for you. Just have to get the right one. This one's right screen. Oh, I have to click share, sorry. Yeah, looks quite good. Okay, before I start the modeling of this timber frame wall, just as an information for you, my colleague probably will share the link also with you. The model, what I'm doing here, has been analyzed and calculated also by hand on our knowledge base. You can find it by the number 001876. And here you can see the formulas that are lying behind it, and also the deformation. And of course, the inner forces are calculated here with hand formulas or equations. Okay, maybe once I've done or generated the model, I will take a look back also to the homepage just to show you what we are doing here. Okay, before we create the model, we have to give a model name, timber frame wall. I will choose type of model 3D here. Then in RFEM 6, one of the advantages compared to RFEM 5 is that you have every design add-on completely integrated into the software, and it's not a separate add-on anymore. It's completely integrated into the software, which has a lot of advantages for speed and also design purposes. And so I can choose or decide what I want to build or to plan in here, and what do we want to do in this first simple structure. I mentioned it already, will create a beam panel. Therefore, we would need the multi-layer surfaces add-on. We don't need the load wizard. We also even don't really need the combination wizard, but it does not matter. and we will do the timber design in the timber design add-on. Looking for the third register in the basic data, we will have the standards here. We are calculating according the timber Eurocode, and of course it is also possible to calculate according American standard, here Canadian, and a whole bunch of others, even Chinese is possible for timber design. Mentioned it, also timber design. We will choose timber design with all the national annexes that are available for Europe, and there it is quite similar. What is possible, America, Canada, Switzerland, Italy, because it has some special rules in Italy related to Eurocode, but different a little bit. There's Chinese and there's Australian standards as well. Okay, all the other options are here not relevant for this quite simple model. Okay, we start and we will create the surface or the wall, and therefore we create a new thickness. For starting, similar as, I don't know if you ever worked with our software, but also when you created a CLT wall or floor, cross-laminated timber, you can start with just a concrete material. That's what I'm doing here. Any kind of thickness that does not really matter. Just create it just for drawing the structure and how it's going to look like. So it has a size of, in X direction, of minus 2.56 meters. Minus 2.56 meters. This is now a theoretical example, and I choose this distance of 2.56 meters. I can maybe also add a little dimension line just so that you saw it here. Maybe in the other area here. Of course, you know, for timber frame walls, you have a standard distance of each beam in the panel of 0.625 centimeters meters, so 62.5 centimeters, which is the standard design. In America with the inches it's a little bit different, but yeah, once again we're doing this here according to Eurocode. I will show how to change it also for the relevant parts of American standard, but yeah, the main purpose here is Eurocode. And just to get back to the homepage again, here the calculations here by the door, or the hand calculations, also based on the Eurocode inside this. Okay, and to see it maybe in this picture, a little bit moving, that because of the distance here, I get exactly 5 beams side by side into this structure. Okay, just for an explanation that you maybe if you ask why I choose such a distance here. Okay, I want height, also more European value of a standard value of minus 2.75. Then I will add supports in it, and the first support should be not movable in X, Y, and Z direction, and also no turning, because it's in this case 2D position. And I will put that to the origin in order to keep it statically determined. I will also just move one support on the right side. In the bigger model that I'm going to do just after this simple model, of course, you would do a complete support underneath the wall. That's for sure. It's just for this first example here. So this one is moving, okay, here, and so that it's not flipping outside of the plane in Y direction, I will define it for the degree of translational degree of freedom in UY direction. Okay, I will put a line load for the first load case of a value of 5 kilonewton per meter and go to load cases and combinations and create a new load case for the wind. I deactivated the self weight just so that it can be compared to the calculation by hand. And here's the wind, and I'm directly assigning a load combination in here manually. That's what I mentioned in the start, that I even don't need the load combination wizard in here, as I'm just typing it for this simple model. Once again, in the bigger example right after this, we have used the combination wizard. Okay, just typed all right, and then it's there. So this is the combination that we are designing. But of course, I forgot to define the horizontal load from the wind. This is going to be a force of a value of 8 kilonewton, and it goes in x direction and minus, of course, because I want it to be moving in this way. Okay, but so far this is still a concrete wall, which we don't need. And how are we going to change it to a timber frame wall? We double click on the surface and yes, we'll edit or create a new thickness. In this case, I'm choosing edit this thickness. And now that I've activated the multi-layer add-on, I can choose here the layers. If it maybe I want it as a CLT wall, then I would have done it this way. But in this case, we want a beam panel. So that's the thickness type for the timber frame walls. Not even pure timber frame walls. You will realize it when I'm in the material database of it via this library book in here. So now it's predefined OSB according either American, Canadian, or European standard. For our example, we would use 10 by 18 millimeters OSB. But if you use the drop down bottom in here, you can also use gypsum, for example. Yeah, even for the timber floors, at least here in Germany, what's used quite often are the Fermacell gypsum fiber boards in order to stiffen out your structure. So that's quite an economic way of creating your walls. So, but yeah, I mentioned it here. I will choose OSB. I can also show you just as an imagination how you would do it with the American standard. It works quite simple, similar to what you choose. I just have not switched my dimensions to inch. So for me, it's rather hard recalculating the 0.5 inch because thickness needs to be defined here additionally. So this is what we will probably better be choosing by the European standard. We have to change the material into orthotropic for this type of thickness, and I will define 15 millimeter thickness in here. All right, so that's the sheeting. I also can make the planking from both sides. I can vary it, so it can also be an unsymmetric. I can even say the sheeting on the other side is made from a different material than OSB. For example, if you are using some insulation material, and this has also some capacities for stiffening out your structure. So this would also be possible to be defined. So the material can be different on front and back of your beam panel. Okay, so this leads us to the framing members. Yeah, here that's the usual material section database that you can choose here. Yeah, sensible, of course, is here only the rectangular one, but just as a notice, it is possible to choose and define any kind of section here. It's just for this case, I'm using a 6 centimeter by 16 centimeter board or beam, inside, and this is the most standard way to do it, and that's what I'm going to do for this example. These special selections I will show in the bigger 3D model afterwards. Then you choose the connection type. You can have nails, staples, or user-defined slip in here. And when we choose staples, for example, with the dimensions of 1.5 by 50 millimeters, you see that the stiffness is already calculated in here. We're choosing a spacing of 75 millimeters. And when we compare it, I hope it's the last time I'm switching to the homepage. If you look into this here, you see that this how this equations or how these values are calculated in here. So with the slip modulus from the mean value of the beams and the planking. Okay, so this gives this value. It would also be possible to consider the connector stiffness just in one direction. So then you have it just in X direction and the Y direction will be 0. I will also show what that means in the generated beam panel. So that's an important info that you should remember once we generated the beam panel. So this, the point what I'm showing you here is this is a generator to generate the timber frame wall in the big program RFEM. Okay, then we have the inner studs in here. Then you can have several, well, you can have other sections in here. That's similar to what I showed you when I was working in the framing members. It counts here vice versa. You can have here IPE profiles if you want. For example, if you have a very high vertical load and you say, okay, in one special part of it, I want an IPE, then you can say, create any distance in here, 1000 millimeters, for example, and create an IPE. So that would be possible to also be defined. All right. But here, yeah, for this example, we are choosing center to center and the spacing that I already mentioned, 625. This offset and what it makes, I will also show in the bigger model afterwards. Okay, but what I'm choosing similar to the definition before is 1.5 and 50 in here and the connector spacing of 75 millimeters. So then I press OK. And one more time, OK. So nothing's changed. Surprise. Why is nothing changing so far? The answer is because I have not shown the beam panel. What we want, or what our idea is from creating the beam panel or for developing the beam panel is that you work with, as you are keen to it, as you know it, with surfaces. And then inside it, you generate the beam panel. And when you now activate the beam panel, you can see that it's generated in here. So here is the beam, top beam and the bottom beam, and also the posts. So we have 5 posts in here. But yeah, obvious because of our distance. I maybe can switch on photorealistic visibility a little bit just to give you maybe a little bit better imagination of what it's doing. I think that I hope that can be seen this way. So you see the OSB is eccentric, moved to the outside. It is connected with this little, now I'm switching the rendering off. It is connected with these little pins in here, which are representing the staples that we have in there. And when we double click on one of those pins, you can see that there's a rigid link defined and it contains the stiffness that we generated in the beam panel. I promise not to show the homepage anymore, but I do it just one more time because it's just good to have it seen in here. if you remember, I had defined a spacing of 75 millimeters, and this is calculated on 1 meter, which gives you 13 connectors. 13 connectors via the calculated slip modulus gives us this value in here. So, and it is done here. And I also told you that we should remember this longitudinal stiffness, where if I had chosen just to have the stiffness in UX direction, my UZ value would be 0 in here. So that would also be possible. Okay, this is the generated hinge there, and it's generated once again between each beam and the OSB planking. I will put on the rendering again. Oops. So here this way, it's probably a better visibility. Okay. So now we want to see results of it, of course. I did not mention the FE mesh. That is something that we should have maybe looked before, but yeah, we can calculate it once again. I will get the rendering off, and you see that the FE mesh in this case is nonsense. So we have to go back to the FE mesh, make it a little bit finer with 5 centimeters, which yeah, is maybe too fine, but yeah, for this example, I think we can do it just to compare our deformations and inner forces. And maybe also the reaction forces, because actio should be reactio. That's what I learned in my studies. All right, so we you see that the FE mesh is now fine, maybe too fine, but it's good. We will leave it this way, and we have a deformation of 3.1 millimeter, and reaction forces, actio, reactio, that works. We have a little bit, because of the eccentricity, small forces here, but I think they can be ignored in this case, which gives us a little bit of a little bit changing inner forces, but not that much. This is the deformation that you would also calculate by a hand for this simple formula. And then now it's actually done. You have the stiffness correctly assigned, so that's all working. Of course, we did not design the timber frame wall. So how would you design the timber frame wall? Then this I can also show you via our new, or it's not new, but in RFEM 6 it's new, the so-called member representative. So if I'm choosing here member representative for the posts, and what do you verify for the post? The buckling, of course. Then you would say, and the advantage of the member representative, in case you have not worked with this with RFEM 6 and do not know this, is in former times you would have to choose all the posts and edit them and work on them. And this is now not necessary with the member representative, because every member that is similar to the other one, which is the case for posts and timber frame walls, can be is summarized in the member representative. So you just do it once, and in former times you did it several times. This is one of the good advantages. And then, of course, effective lengths, what we do not verify, lateral torsional buckling. We even do not need to verify the buckling about the minor axis, because that is covered by the planking or by the sheeting. But yeah, just for sake of completeness, we are verifying it. Then we switch to the add-on timber design, which is right here in the drop-down menu. Once again, it's one of the new advantages of RFEM 6 is that you do not have these add-ons here on the left side anymore. I mean, you have here register timber design, but you do it more about the columns because it's completely integrated into RFEM 6. Okay, what do we verify? We want to verify this member representative that I just showed you. So that's member representative 2. And then we calculate it and look for the results. As I said, what we want to verify here is buckling, pressure against lateral to the grain for the downstand beam is also possible, but it requires the definition of an additional beam. That's why I'm skipping this in here, just as an information in case you ask yourself this question right now. Okay, you see stability even works in both direction, and yeah, to show you also that the verifications are done, and we are very proud about how these verifications are shown now. Here you see that all the equations are there with nice written formulas, and of course you get the slenderness rate and the buckling factors, and this can directly be put into the printout report and is your documentation of the results in what you have calculated here for the posts. Okay, the connections inside it is something which is also the most important verification. It must be done by hand, but there are methods and ways how that help you to calculate that. And you can take a look into navigator results, static analysis, releases, and then line hinges and forces. So usually the value that you need, we'll switch off this one and also the rendering once again. So you see in here, well, in the middle there's nearly happening nothing, and it's rather a constant value. So when you are very much on the safe side, you would calculate it, your load bearing capacity of your staples in this case, and compare them with a value of 3 kilonewton per meter, or you could also take the middle value of it. This is what the software gives you, and we're working also on designing them. Of course, this will also be possible quite soon. Okay, this is the simple model. In case there are no questions unanswered, there is a question, what about the possibility to add openings? Yes, that's what I'm showing you now in the bigger model. So that's a good question and leads us to the bigger model. Therefore, I'm closing this and switch to the bigger model. It is a house that I probably have been shown here since 10 years or something like that, I think. So if you take a look to the historic structures, this is something I probably showed 10, 15 times here already. It is completely made from CLT. Here it has a little balcony. It has a length of 8 meters, width of 10.8 if you include the balcony outside it. It is all the CLT plates are connected with hinges in here, and also in here on the wall they are also connected with it. Not the surface. I wanted to take a look at the line hinge. Here's one here. Okay, so there should actually be also a slip in X direction, and you get it's similar to what I showed you in the smaller model before. Then you get the forces in the line hinge and have to compare them with the load bearing capacity. Okay, so now this CLT building has openings here, of course, and I want to change maybe this wall and also this inner walls into a timber frame wall. Before I'm doing this, what you would have to do in order to regard the opening is to separate this surface into several surface cells. And for this, we have a new function in here. It's called extend trim line to next member line. So we say okay, and then you see that it's divided in here, and I have now this surface cells in here. Surface cells are quite a new object in our software, which are useful on a whole bunch of elements in the software. And we are using it now also for the beam panel. You probably know that, at least when I'm working according to Eurocode, that there is, for the timber frame walls, there is a simplified approach according to chapter 9.42a or something like that. Don't get me. I'm not 100% sure which chapter is, but it's 9.9.4 something. And this is for a hand calculation. And what would you do when you calculate such a structure by hand? You would calculate your horizontal force, and then you would say, okay, this surface cell will bear this horizontal force, and this surface cell will this, and I need inches here and here on this point, and I'm totally skipping the elements in here. Now that we are generating such a real nice 3D object, it is not necessary anymore, because we are calculating about according to in Eurocode it's 9.4 B, the method B in the Eurocode, and especially if you're calculating about according American standards, they even don't know the simplified approach things. They are always calculating without dividing such elements. They are always using the more advanced design, I would say. Okay, and I will generate the beam panel just right away, and then I will also mention a few more points what you could do in here. Maybe, what I could do is that maybe I would delete this one and divide the surface, the bottom surface here on one point, just to show you what you can do by regarding slip and what you cannot do, and where the difference is to the top, where I'm still having one continuous surface. Okay, therefore I go right click and say divide surface with intersecting lines, and now it is divided, so that's quite simple. And I'm just doing it on one side just for demonstration purpose. So extend via copying. So here I'm leaving the cells. Okay, I'm quite curious what's coming out of this, because I've never tested it before. And I will insert now an object line hinge dialog box. Give it also my favorite slip of 8,000 kilonewton per square meter, and say, okay, I'm here and here and oops, and god damn it, and here I'm having the slip. So that's quite similar to what I've done here on the walls, on the CLT walls. Sorry. Okay, I forgot to mention the load, by the way. So we have self weight in here. So quite simple, 1 kilonewton per square meter over even the complete balcony. And in the load case 2, I have 1.5 kilonewton per square meter. And here in the load case 3, I have generated the wind with the wind load blowing on the building from this side. No, sorry, from this side, from the front of it. So that's where I'm stiffening out my structure, just for your information. And of course, I choose an automatic load combination and generated all these load combinations that we are using in here. Okay, so a lot of words I said. Now I can go and maybe just display our relevant walls, so these ones, and go here into the selection and define edit surface and choose the beam panel we just defined. Yeah, I will go to the edit or to the dialog box. Just once again, I've changed the sheeting on the other side, but then it is quite dissimilar what we've done before. Framing members are the same, and oops, hoppala, sorry. We're using also staples, and I'm keeping now the removing framing members, and also the distribution, and this offset here is by 0. So then I'm generating it and press OK. And then you see that this one is generated in here. This one's not. There was a small problem. Yeah, I should have, sorry, no. It's not working because I have not divided it. Okay. I said I would be curious what's happening in it because I never tried it. I probably should have tried it, then this would not have happened. But anyway, okay. So now we look for the top floor at the top wall at first, and we see that now the distribution of the beams of the post is quite good. We would calculate the opening, and it kept our spacings of 625 millimeters in between, and here we have a middle value of 100 millimeter left, and this is also good because we still can get insulation into it here. But yeah, I said it. What I wanted to show you, what this special selections do in here. So if you remember this, so this is a post coming down in here, and if you do not use the remove framing members from smaller inner cells in here, choosing apply, and here then you would, I hope it can be seen because it's highlighted now, but you see there's now an additional post which makes no sense. So this is actually what this selection does here. And in case it does maybe not fit, or you want a bigger distance here beside this, you can have this offset for the first stud. Once again, here I don't think it makes sense, but if you want, you can choose it, and then you are moving the first stud by 6 centimeters, and then it's maybe I will do it like this. It can probably be seen. So this, and we go apply. So you see here I have now 6 centimeters less. So, and then I can put, of course, more insulation. This is how this works and how you can assign that. Okay. Yeah. Now, when we talk about openings, the point is, it's in Europe. I don't know how it is all over the world, but in Europe we have special rules what you can do on such bigger openings. Maybe you also have a complete door that's going to the bottom. If you have a balcony here on this side, just you can imagine 100 of variations of it. Then you what we do here in Europe is that we are using the top beam, or how you call it, on this window, and move it to the next stud. That's one of the possible constructions, and then it's a complete shear stiff, and it's, of course, it's nailed on every part wherever our OSB plates are connected there or coming together, and there's always a beam or a post behind it. That's where it can be nailed on. That's for sure. Or what I did here in the bottom, and that's what I mentioned from the start. If you want, you can connect the beams, and then they have a slip in between. So the slip is what I showed you in the first example, between the OSB and the post, and between those two timber frame walls. So that's the way how it can be connected. So it's maybe a little bit hard to explain, but maybe after the board, download the model, take a look on it, then I think it should be quite easy to understand. Why it's not calculating? Just hold on. I mean, we necessarily don't need. That's strange. Okay. Wait, maybe I will not get it going. Hold on. We will get rid of this. Maybe we will not divide it. Go in here. Because maybe this was the reasons for it. Okay. This, oh no, it's still intersecting. So in here, and now if we do it again, oops, was too quick, sorry. Up and here, edit, and choose again the beam panel. Okay. Why is that now? Ah, so I forgot this one. Okay. So we need to extend here one more try, and otherwise I will leave you without the results of it. But I think it can work. Yeah, should be. Okay, it's not a real small structure, not even a big structure, but yeah, I also use the building model inside just to get my masses all around. So masses maybe also a good point. One other advantage of using such a 3D object is that you can use the stiffness of the timber frame wall similar as CLT for every calculation. So also for your dynamic analysis, you can create response vectors and use it for this. Okay, and you see in here, so this is now quite similar to what we have before. We have the deformation, we have the inner forces of the beams, and can do the verification, of course, on it. Okay, that's it. That's all I wanted to show you. Quite a short webinar, I think, but yeah, 43 minutes was not that short. I hope my colleague was able to answer all your questions. I'm not so sure. Maybe, Andreas, do you have something open I should maybe mention, or?
No, I answered quite all the questions.
Good.
Maybe there are newer questions when I take over. Maybe you can answer the
Okay.
rest questions. Okay, I share my screen. Yeah, thank you for your presentation, Bastian. An additional hint from my side, you can book your free online appointment, such as a product demonstration of one of our products like RFEM, RSTAP, RWind, RSection, or any add-on. Just contact our sales team via clicking that link at the bottom, or you can scan the QR code. You can download the PowerPoint from our website. In the next days, you will get an email with your attendee certificate with a link to the website and the recording, where you can find also the PowerPoint slides and the provided models. Okay, That's also all from my side. Thank you for your attention. Thanks again, Bastian, for your presentation. I hope we meet each other in a future webinar. Yeah, have a nice rest of the day. Bye-bye.